All right, work, energy, and power, unit number 3. We've talked about so far work, we talked about energy, we talked about total mechanical energy, the difference between potential and kinetic energies, and we talked about how they calculate these things. So next thing that we're going to talk about is this conservation of energy. So part number 4, conservation of energy. We have some learning targets for this video. First one is I know what conservation of energy is. Pretty straightforward. The second one, much less straightforward, is I can solve conservation of energy problems. That's where things get kind of hard. Conservation of energy is where this unit takes that twist and starts getting rough. This is similar to in the first unit we talked about forces, and there were different forces, and we can calculate these forces, and then we said let's use Newton's laws and solve problems with it. This right here is similar to Newton's laws in the last unit. This is where we put all those equations together into a picture that's cohesive, and we can solve for unknown variables and things like that. So we will start off by basically just talking about conservation of energy. So number 1, conservation of energy, or point number 1. What is conservation of energy? There's a simple equation that both gives you what the qualitative and the quantitative description of conservation of energy is. That is delta E is equal to 0. That is a very, very profound statement. Delta E is equal to 0. It's very succinct, very short, doesn't take very long to write it, and it tells us a ton of information whether we know it or not. If you remember from unit 1, I said we could have delta something like delta x, and that would be x final minus x initial. We could have delta v, which would be velocity final minus velocity initial. We could have delta force, which would be force final minus force initial. Delta anything, we can delta anything we want. But for energy, that gives us that our E final minus E initial is equal to 0. If I add an E initial to both sides of this equation, then my E initial minus and my positive E initial, those cancel, or they subtract to 0. And what I'm left with is that E final is equal to E initial. And this is going to be like the big starting point for most of our problems when we talk about conservation of energy. This will also probably be the starting point for most of your problems when you do the work energy theorem as well. But when we say E final is equal to E initial, I talked about the total mechanical energy being E. So E final, hidden inside this E final, is actually 3 or 4 different things. So E final is the kinetic energy, T, plus the sum of potential energies, which we're calling U. And since this is our final, we'll call it T final and U final. So energy final is equal to energy initial, which is T initial plus U initial. You don't need to go through all these steps to get your answer to use conservation of energy. I'm just being careful about it, and I'm showing you all the steps. But if you were to skip several of these steps, that's okay. Our T final, we'll just leave that as T final for now. But our U final, that's going to be U spring final plus U gravity final. Our T initial stays T initial, but our U initial, that's going to be U spring initial plus U gravity initial. And so this is really another very good starting point for a lot of these conservation of energy equations. In fact, if you didn't do this or this, and you just started here, that's perfectly fine. We can go one more step further and replace our T final with 1/2 mv final squared. We can replace our U spring final with 1/2 kx final squared. And our UG final will be mgy final. I'll do the same thing to my initials. So I get 1/2 mv initial squared. I get 1/2 kx initial squared. And I get mgy initial. Now I'm going to subtract T plus U from both sides. So I'm going to subtract T initial and U initial from both sides. What I'm saying is that this is the shorthand form, but what I'm really subtracting is this whole thing. I'm subtracting 3 terms. I'm subtracting a 1/2 mv initial squared, I'm subtracting a 1/2 kx initial squared, and I'm subtracting an mgy initial And when I do that, this side goes to 0, and I get 1/2 mv final squared minus 1/2 mv initial squared. I get a positive 1/2 kx final squared minus a 1/2 kx initial squared. And it looks like I'm gonna run out of room here. Try to fix that up a little bit. There we go. All right, then I have a positive mgy final minus mgy initial. All of this equals 0. But what I have here, I'm going to underline these first two terms in blue. I'm going to underline the second two terms in red, and the third two terms I will underline in green. So my blue terms, actually let's write this as well, 7. My blue terms, those are going to be 1/2 mv final squared minus 1/2 mv initial squared. What if I factor out a 1/2 m from both of those? I would get 1/2 m times v final squared minus v initial squared. And then on my red terms, I could factor out a 1/2 k. And so I'd 1/2 k times x final squared minus x initial squared. And my last terms, I can factor out an m and a g from both things. And I get mg times y final minus y initial. So this blue stuff is going to be basically t final minus t initial, right? So I can rewrite that as delta t. The whole term will be delta t. My red stuff, that's basically delta u sub s. There we go. Had to think of all the letters in the alphabet first. And then my stuff in green, that's going to be delta u sub g. And all of these things, when I add up these three changes, I will get 0. And so it tells me a lot of things that maybe aren't quite clear to you. So let's talk about some of those things that it's telling us. First of all, it's telling us that energy, when we use conservation of energy, that the energy of the system doesn't change. It is the same before and after. These two values are the same, right? Furthermore, it tells us that our T final, our US final, and our UG final, they don't have to be equal to each other. That's right, they don't have to be equal to each other. So my U spring final doesn't have to be equal to my U spring initial. My UG final does not have to be equal to UG initial. But when I add all three of those energies up, they have to be equal to the sum of all the other three energies. So if I add my final energies up, U spring plus UG plus T final, I have to get T final, I have to get that equal to T initial plus U spring initial plus UG initial. Otherwise, it's not a conservative system and something has happened. So conservation of energy means that our energy doesn't change. The system's energy stays the same. This isn't something that really happens very often. In fact, the only time it happens like a perfectly conservative system is when we talk about the Coulombic force and charged particles interacting. Outside of that, it's not going to happen, right? There's always going to be friction. There's always going to be something doing work to remove some energy from the system, and it's always going to remove energy from the system. That's actually one of the second law of well, it's a result of the second law of thermodynamics. But another thing that it tells us is that when we calculate our change in temperature, or change in kinetic energy, and our change in spring energy, and our change in gravity energy, and we add those three changes together, we should get 0. Which means that one of them is going to have to be negative. And some of them will be negative, and some of them will be positive. But it tells us that my final kinetic energy, maybe I'm starting off with all kinetic energy, and I'm throwing a ball really hard, and I've thrown that ball horizontally, and it rolls horizontally on a surface. And so maybe my UG doesn't change. But what will change is my spring energy and my kinetic energy. So I roll this ball, it hits a spring, and it compresses the spring. That spring energy that's stored in the spring now, once the ball is fully compressed the spring, that's going to be the same amount of energy as the kinetic energy of the ball to begin with, in, as far as conservative systems go. So our energy can change form. So our energies can change form. For example, kinetic to spring energy, or spring back to kinetic. Sometimes we can go kinetic to UG back to kinetic. Sometimes we can go from UG to spring and then back to UG, right? But the idea is that they are changing form, but none of that energy is being removed from the system. It's always still there in the system. And the total change in energy, if I add the before and after together, or sorry, if I subtract the final from the initial, I should get 0. So conservation of energy tells us that if a system has forces that are acting within the system, then the system is conservative and there's no change in energy. So let's kind of write that as a clear statement. If forces act internal to a system, they do not change the energy of that system. Which means that Newton's force, or Newton's third law, those force interaction pairs that we had, those don't change the energy of the system. And that makes sense because they cancel out. When we add all the forces together between the two masses that are, maybe we have two blocks that are pushed up against each other, and we're pushing on one block and it pushes the other block and causes an overall acceleration of this whole two mass system, that interaction between those two things, that cancels out and goes to 0 when we add all those forces. And the same thing will happen when we talk about the work that those forces do. They will cancel out work for work and they will cause 0 overall work. Therefore, the internal energy of the system does not change. So forces acting internal to a system do not change the energy of that system. That's why when I was talking earlier in one of the previous videos about throwing a ball directly up in the air, if I define the system to be my hand plus the ball plus all the air and earth, then I will have a conservative system. When I throw that ball up, it'll go up to so it'll start off with all kinetic energy and maybe a little bit of potential because it's leaving my hand instead of from the ground. But it will go up to some maximum distance, and during that time, all of my kinetic energy that I gave to the ball to begin with from my hand is converted to a gravity potential energy. So I exert a force on a ball, it goes up, that energy that it has is kinetic, it gets converted to potential energy due to gravity, and then it reaches that turnaround point, and then it falls back down. And so gravity now is doing work. Well, it's not really doing work. Gravity is doing something to change that energy from gravity potential energy back into kinetic energy. And so once it reaches my hand again, it'll be going that same speed. And I talked about this in the kinematics unit 1, where if I throw a ball up and it's perfectly parabolic motion, when it reaches that same height again, it'll be the same speed, but now negative. And this is why, because that energy is going from kinetic to potential and then back into kinetic energy. So the thing is that the gravity energy is not outside of our system if we define the Earth to be part of our system. And so that is a conservative thing. But also that drag force that will slow it down, even though it's a dissipative force, it will result in heat energy increasing. It'll cause the air around it to heat up a little bit, and that's where that drag goes. And it'll eat up some of that kinetic energy, but overall, that whole system with the air and the earth and your hand and the ball, that whole system has the same amount of energy. It's just some of it's been converted from kinetic into gravity, and then from gravity back into kinetic. Some of it was lost to drag force, but that becomes just thermal energy that's within our system as well. And so no work is done. That's why we talked a little bit about what system should we choose, because we need to be clear about what is a conservative system versus what is a non-conservative system. And a conservative system has only conservative forces acting, and all of the forces in it are internal. A non-conservative system can have non-conservative forces acting, but they are usually external forces as well. So friction would be an external force. Friction would be a non-conservative force. Drag force, usually we wouldn't consider that, but if we did, it would be an external force. We wouldn't include the air in our system, and so we just let the energy be lost. We don't know where it goes. We don't care. It's just gone. Some drag force is doing work to slow our ball down. So in general, when we do these conservation of energy problems, we start off with just setting up a statement of conservation of energy and then slowly picking it apart to try to pull out useful information. And that would be like saying delta E is equal to 0 is our starting point. So E final is equal to E initial. So U final plus T final is equal to U initial plus T initial. So that means that UG final plus US final plus T final is equal to so forth and so on, until we get to the point where we have an actual equation where we're replacing T's with 1/2 mv squares, UG's with 1/2 kx squared, or sorry, with mgy squared, and U sub s's with 1/2 kx squares. So let's try a example or two. For example one, let's say that we take a ball and we throw it up. Actually, let's before we even do that, let's talk about if I were to throw this ball up with some initial velocity v initial, and we'll say it's 10 meters per second. And we know the mass of this ball is 150 grams or 0.15, that's ugly 5, 0.150 kilograms. I throw this ball up with 10 meters per second, and we'll start from some distance h above the ground. That's my scenario one. For my second scenario, I'm going to start off at the same distance h above the ground, but now instead of throwing it up with 10 meters per second velocity, I will throw it down, and so my velocity initial is now negative 10 meters per second. My mass, it's the same ball, so it's still 150 grams or 0.150 kilograms. My question to you is, which one of these systems has more energy? Is it going to be the first one because it's being thrown up, so we give it that additional gravity potential energy? Is it going to be this one because we've thrown it down, so it gives it that extra initial kinetic energy? Or is it going to be the same between the two? So I'll give you a moment to pause the video, try to figure it out, and we'll be back with an answer. Okay, so if you figured it out, the answer is they're the same. Well, let's look at the equations for our energy. We know that, this situation will have UG, which will be equal to mgh. And this will also have a kinetic energy of 1/2 mv initial squared. This side, I'm going to call it scenario 1, so T1, UG1. On this side, we'll have UG2, which will be the same, mgh. And then on the T1, or sorry, the kinetic energy, T2, is going to be 1/2 mv initial squared. When I plug in my v initial squared here, or my v initial, it's going to get squared. And so if I plug in a 10, I will get 100. If I plug in negative 10 on the T2 side, then I will get negative 10 times negative 10 is positive 100. Mass is not negative, 1/2 is not negative, and so the T2 is going to be equal to T1. Also, mgh is mgh, and so those are the same. So if I look at these two situations, it would make sense that these have the same amount of energy in them. Or it should, as far as the mathematics tells us. But let's look at that first scenario just a little bit more. I start off from some distance height, some distance above the ground, h. I go up, and I know it's going to be like straight up and down, but I'm just doing this side-to-side stuff to show you. But once I'm at this point here, I'll go from this position where all of my energy is mgh plus 1/2 mv squared. I'll go up to this top where now all my energy, I'll call this E1, this is E0. E1 is now mgy2, where y2 is the maximum distance above the ground. And then it'll go down to this point here, which we'll call E3. So when I'm at the top of my motion, I know that my vertical velocity is going to be 0. So when I plug in my 1/2 mv squared, it's just 1/2 0 squared, so that's 0 and that goes away. So all of my energy, my total mechanical energy at the top is just mgy sub 2. For E3, I will have the same mgh that we had before because we're at that height h above the ground, but then I'll have plus 1/2 mv squared. That v squared there, that's going to be the same velocity, but negative. It's going to be the same velocity as what we had to begin with, at v naught, I guess. It's going to be the same velocity, but negative, pointed downwards. And so this thing here is going to be the same as E sub 0, which was also mgh plus 1/2 mv squared. So that's why they have the same energy, because when I'm talking about this ball being thrown up, it goes up. It converts all that velocity into that kinetic energy and that velocity. It converts it into potential energy and gravity, and then the gravity does work, or gravity does something to increase its kinetic energy again until it reaches that same height above ground where the velocity is the same as it was to begin with, but now negative, and so the energies are the same because they are scalars. If they were not scalars, they would probably be different because of that directional thing on the velocity, but they are scalars, and so this means the energy from point 0 is equal to the energy in 3. And so those two scenarios are the same energy levels. And what we have here is that this part, once we've done this first part of the motion, let me do that in red. Once we've done this first part of the motion, what we've done is we've basically created scenario 2. So scenario 1 has scenario 2 in it. And we talked about path independence. It doesn't matter how you got to that point. What matters is that you're there and where you started from. So really, the only time that something interesting is happening is here for both of those motions. So just a quick little mess with your mind type of thing. But let's go on to another example. And you'll see a little bit more about how these energy things can be kind of interesting. Okay, number 3A. Okay, so 3B. Let's say that I have a mass and it's attached to a spring. So here's my spring, my wall. I attach a mass to a spring and I stretch out some distance. So here's my natural length, L sub 0, and my distance is x. So, sorry, this distance here between these two things is x. So well, I've stretched out this distance x, and I will have some certain amount of energy, and I will let it go. And it's going to, and this is a frictionless surface too. I should say that, frictionless horizontal. So if it's a frictionless surface, there's nothing to remove energy from it. And this is just going to change between kinetic and potential energies back and forth over and over and over again. And it'll keep doing that for, until the end of the universe, because it is frictionless and perfectly conservative. Of course, this only exists in our mind, but it's a good introduction to things. So what I'm going to do is I'm going to look at my energy initial. So this is our initial situation. We'll call this E sub 0. And E sub 0 has a spring energy because it's stretched some distance x. So we have 1/2 kx squared. Actually, we'll just call it U sub s for now. So it has US sub 0. And when it comes to the kinetic energy, well, when I release this and I let it go, I'm releasing it from rest. And so my velocity initial, or V0, is 0 meters per second, which means my kinetic energy, T, is 1/2 times m times 0 squared. So our kinetic energy is 0. So all I have in my energy to begin with is just that spring energy. At some later time, maybe it will make the spring will pull the mass back, and then the mass will be sitting at the length L naught, and so the spring is no longer stretched. When the spring is no longer stretched, it does not exert a force, and so there is no US 0 because kx is 0. Because x is 0. So if that's the case, then our E1, we'll call this the energy of position 1, E1 is just going to be equal to our kinetic energy. Now, again, looking at kinetic energy, that is 1/2 mv squared. If I split this energy up in any way, shape, or form between kinetic energy and spring potential energy, I am always going to do it by taking away velocity. I can't change my masses. I mean, I could, but that makes things so much more difficult. So we'll say constant mass, but the velocity can change. And if the velocity changes and it goes into some other type of energy, it will get smaller. And so when we have all of our velocity or all of our energy in kinetic energy, so when all energy is kinetic energy, our velocity is the maximum velocity that that system will have. Of course, it'll reach that velocity many times, right? It'll just keep oscillating back and forth forever because it's frictionless horizontal surface. But whenever it passes that L sub 0, we have no spring energy and maximum velocity. So we also have our maximum kinetic energy. I don't like that. Let me rewrite that. Maximum kinetic energy. So what I've done here is I've illustrated two different positions on this motion, but I chose these two for a reason. I chose the first one because our velocity is 0, and so all of our energy is in spring potential. I chose the second one because our stretch distance is 0, and so all of our energy is in kinetic. So I'm going to ask you to solve this problem. Well, not really solve it, but to find an expression for the maximum velocity. What you should do is you should set up a conservation of energy situation. So we have delta E is equal to 0, or E final is equal to E initial. Remember, E is the total mechanical energy. That's the sum of all potential energies. So US plus UG plus the kinetic energy. So T plus US plus UG. Set up a conservation of energy. Obviously, this is going to be a horizontal situation. It's going to be moving entirely horizontal. So maybe you should keep that gravity energy. So plug it in there, make sure it goes in there, and then just plug in mgy, and we'll just say that this position here is y is equal to just y. And so you can call it mgy for both of them, and then see what happens with them. They should just go away. But find an expression for the maximum velocity. So plug in your kinetic energy, your potential energy, your spring energy equations, solve it for V max, and then see what you get. So I'll give you a few moments, pause the video, give it a shot. Okay, so now that you've had a chance to work on it, let's go ahead and get a new page where we have 3B. So we'll finish off 3B. The position 0, E0, that's when we have the spring fully stretched and there is no velocity. And so E0 is equal to T0 plus U spring 0 plus UG0. Our E final, we'll call it E1, that's when we've the spring is no longer compressed and we have all of our stuff is in kinetic energy. And so we have T1 plus UG1 plus US1. Our conservation of energy statement says that E final, or E0, is equal to E initial, or E1. I guess it doesn't matter, you can switch them around if you want, because it's going to oscillate back and forth. And so who's to say that stretched is the final? It could be the initial, because we're going to stretch, and then the spring pulling it back will create the E final being E1. We could also say that it's gone through E1 and now it's stretching things out. And so E1 is then E initial and E0 is E final. So it doesn't really matter what order you put them in, which one you call final, which one you call initial, as long as you keep everything together. So I'll replace my E0 with my T0 plus U spring 0 plus U gravity 0. That's equal to T1 plus U spring 1 plus UG1. What I'd said in the previous videos, and even in this video, I think, was that we're kind of picking apart this conservation of energy statement. We're trying to pull out useful information. So what I've done for my first pulling out is I pulled out all three of these statements: U spring, U gravity, T1, U spring 1, U gravity 1, and the same thing for the E naught. Now, what I'm going to do is I'm going to replace my t's with the equations for kinetic energy. So that would be 1/2 mv naught squared. I'll replace my us's with my spring energy, which is for the zero case, 1/2 kx sub 0 squared. And for ug, well, it's at that position y that we said, so we'll just call it mgy. And we don't need to worry about it being y0 or y1 because it's always the same y. It's a horizontal oscillation. So y0 is equal to y1 is equal to y. Then for t1, I will call that 1/2 mv1 squared. For t or us1, I'll call that 1/2 kx1 squared. And for ug1, we'll call that mgy. So here, what I was saying is that you should see the gravity one just go away because there's no change in gravity. This gravity this gravity potential and this gravity potential are the same number. And so the first thing I'm going to do to solve this is I'm going to subtract mgy from both sides. So my positive mgy subtracting from mgy, that gives me 0. I get the same thing on the other side. And what I get after that is 1/2 mv naught squared plus 1/2 kx naught squared is equal to 1/2 mv1 squared plus 1/2 kx1 squared. Okay, so we had some of these things go away just because of our situation that we chose. Initially, for the 0, we were pulled all the way out, so we're maximum stretch distance, and our velocity is 0 because we're going to release that from rest. And if velocity is 0, then 1/2 mv squared is also 0. For the E1 position, we had a stretch distance of 0. So kx squared is going to be 0 because x will be 0. And I can write my next line of algebra as 1/2 kx sub 0 squared is equal to 1/2 mv1 squared. mv1 or v1 squared is the same thing as our maximum velocity. So I'm going to call it vmax squared just for illustrative purposes. You don't need to do this if you don't want to, but you should know that one of these velocities is usually going to be your maximum. When we do a problem with a spring oscillating like this, we're usually going to pick one of the positions where it's either all spring or all velocity. So here's that happening. If I multiply both sides of this equation by 2, my 2's cancel my 1/2, and I get k times x naught squared is equal to m times v max squared. I want to solve this for velocity. And to do that, I have to just basically divide both sides by my mass first. To do that, I will get Vmax squared is equal to k over m times x squared. Next, I just need to square root both sides. My result is that Vmax is equal to square root k over m times x. So my x was squared, it got square rooted, but my k and m, they are not squared, and so I'll just leave them inside the square root. This equation here is a pretty significant equation for a lot of physics. Just want to move that x or make it look a little nicer. So this Vmax is equal to square root k over m times x. There's this little square root k over m thing. And this is your answer, right? This is an expression for Vmax in terms of everything else. You would, in a problem like this, you'd be given x naught, you'd be given m, you'd be given k, and you'd be asked to solve for your maximum velocity, or you'd be asked to solve for k or m or x or something like that. But your result should have something similar to this. So if I multiply both sides of this equation by square root m over k, I get square root m over k times Vmax is equal to, well, those square roots stuff will cancel out, and I'll just get x. And I'm just going to get rid of these subscripts for now because we're talking kind of less about this problem and more about things in general. And this equation that I've written right here, and let me write it or circle it with a different color. That I've circled in red, this equation is really, really, really important for these types of systems where we have an oscillating mass. Let's look at those units on inside the square root. So I have the square root of mass, which is kilograms, divided by k. If you remember, k is newtons per meter. A K constant tells us how many newtons you'll exert after stretching a certain number of meters. So pulling things out a little bit, I get my kilograms, and my newtons becomes a kilogram times a meter over a second squared, and we still have that 1 over meters. So my kilograms cancel, my meters cancel, and what I'm left with is the square root of 1 over second squared. Our rules for dividing by a fraction say take the bottom fraction, multiply the top by the reciprocal. And so that'd be taking 1 over s and flipping it, and we get 1 times s over 1, which is the square root of second squared, or seconds. Why am I talking about this square root thing, and why does it have units of seconds? Well, there's an answer for that. If you've ever wondered how many seconds it takes to oscillate, you would be wondering about a frequency. It turns out that this square root m over k thing has a special purpose. I'm going to call it omega. Sorry, I'm not going to call it omega. I'm going to call it 1 over omega. If I multiply both sides by omega, I get x times omega is equal to v. In other words, what that tells me is that if I take this distance here, this stretch distance, and I multiply it by the frequency, I will get my speed, my maximum speed. And if I know my velocity and I divide it by omega, I will get my distance. This omega has a special name. It's called the natural frequency. And omega is equal to 1 over 2 pi times the regular frequency, what we call the linear frequency, f. And so this is a really, really important quantity. It's super, super useful to use. And it's a good idea to see it now, because once I start talking about rotational motion stuff, we'll get this equation that says v is equal to r times omega, which looks an awful lot like this and this. Well, not that. It looks a lot like this and that, right? If I replace x with r, then I have that same equation. And so this is a really important link between the rotational motion world and our regular linear motion world that we've been talking about so far. So in the future, we'll go into more depth about that. The ultimate result that we get here is that Vmax is equal to square root k over m times the x0, but x0 is also something special too. x0 is the maximum stretch or compression distance. So what we get is our maximum velocity is equal to square root k over m times x max, or x max is equal to square root m over k times v max. And we can calculate the maximum velocity if we know how far we're stretching the spring or compressing it. Okay, we'll do one more example, 3C. And this example will be similar in a lot of ways. If I throw a ball up into the air with some initial velocity, and I want to know how high up it is in the air, how high up it will go. I'll start with some distance h above ground, and it'll go up to some maximum distance. Let's say that's going to be y. And then it'll, so it goes up and then it comes back down and it falls back to the ground. And I want to know what is that distance that it will travel up. So I'll call this other distance here from my starting point to my top. I will call this delta y. I want to know what delta y is. If I want to do that, I would have to set up a conservation of energy. So delta E is equal to 0, or E final is equal to initial. I would plug in all my energies and stuff like that, and then I would go from there and try to solve this. So I want you to go ahead and pause this video, take a few moments, try to figure out an expression, so all algebra stuff, an expression for delta y. So if I were to plug in all the other things, I would get my delta y answer. So go ahead and give that a shot. Pause the video. Okay, now you're going to try. We'll go and walk through this. Our final energy is going to be the energy at the top of the motion. And at the top of the motion, what energies will I have? Well, I'll have T final, I'll have UG final, and I'll have U spring final. At the bottom of the motion, or at the beginning of the motion, I will have T initial plus UG initial plus U spring initial. when I don't have a spring, that's like saying I have a spring, but the k constant is 0. And so my 1/2 kx squared for both these spring equations, those go to 0. So I'm left with is T final plus UG final is equal to T initial plus UG initial. Next thing to do is to replace our T's and U's with their respective equations. So for kinetic energy, that would be 1/2 mv final squared plus mg delta y, or sorry, mgy. We said y is the maximum distance reaches from the ground to the top. So mgy is the energy that it has to begin with, or to end with. And then for our initial velocity, that's going to be, or initial kinetic energy, that'll be 1/2 mv initial squared, and our initial gravity will just be mgh. Okay, last thing to do is to start plugging in some zeros. I know at the top of the motion, my final velocity is going to be 0, so that goes away. And I know my mgy thing, I know something about that. I know that just from the picture that I drew up there, I know that y is equal to delta y plus h. So here's my y, that total distance is equal to delta y here plus h. So I can rewrite mgy as being mg delta y plus h, which is equal to 1/2 m the initial squared plus mgh. I can FOIL out this, so I'd multiply mg to delta y plus mg multiplied to h, which will be equal to 1/2 m the initial squared plus mgh. That's interesting. I have an mgh on both sides. What if I subtract it out? They both go to 0, and I get that mg delta y is equal to 1/2 mv initial squared. And it's almost like that initial height doesn't matter to us. When we talk about conservation of energy, when we talk about work energy theorem, that initial height oftentimes doesn't matter as long as we stay above that position or below that position. So since we're not crossing that path, or we're not going up and then back down to our initial position and then below it, since we're not doing any of that, our delta E stuff, our conservation of energy stuff, is going to subtract out that initial bit of energy due to gravity, because it's the same for both situations, and so it just subtracts to 0. Then I'm asked to solve this for my initial velocity, so maybe I can divide both sides by mass, and I get I was asked to solve this for delta y. So I get g delta y is equal to 1/2 times b initial squared, and then I go and I say delta y is equal to 1 over 2g times v initial squared. Some of you might say, hey, I've seen that before. I've seen that equation before. And yes, you have. In fact, you saw it as v final squared is equal to v initial squared plus 2g delta y. If I were to rearrange this thing, it's like saying that my v final is 0, and go through, rearrange it, and I will see that my delta y is equal to v initial squared over 2g. So when we do these energy equations, a lot of times, or at least these conservation of energy equations, a lot of times you will see a kinematic equation or a result from your kinematic equations pop out at you. And there's some really super cool ones that happen later, but we'll get to those later. So this would be the answer that we're looking for. Delta y is equal to v initial squared over 2g. If you know your initial velocity, you know how high up you will go. But the great thing about this is that it's a scalar. And so if I want to talk about stuff that happened after it passed below that initial height of h, I could do that very, very easily. Whereas with kinematics, I'd have to split it up into 2 separate pieces, or I'd have to set my my parabolic motion equations in such a way that it worked out right. I don't have to worry about doing any of that with energy. I just go through this process, and in the end, I will get a good answer every time if I do it correctly. So that's it for our discussion on conservation of energy. I'll probably have some video come up about practice problems and all that stuff, and maybe some interesting things that happen when we do these conservation of energy. But for now, we're about to hit 45 minutes, and I should probably stop this. So we'll see you in a future video. Have a good one.